Vot Tochner Естественный перевод на английский. On October 3, 1967, at 2:31 and 59 seconds p.m., Major Robert Jack Mitchell of the U.S. Air Force pressed the ignition button inside the narrowest and most dangerous cockpit ever built by man. At that precise instant, the reaction motor's XLR-99 rocket engine awoke with a fury no human had ever experienced before, unleashing power equivalent to 600,000 horsepower that began pushing the metal structure of the North American X-15 towards speeds that defied all known laws of physics. The instruments on the control panel went berserk as the needles spun so fast it was impossible to follow them, registering figures no pilot had ever seen in a manned aircraft. The external temperature of the fuselage reached 1,300 degrees Celsius in a matter of seconds, turning the aircraft's surface into a metallic inferno that was literally beginning to melt around its pilot. Mitchell felt his pressure suit fighting against forces trying to crush him into the ejection seat, while the blue sky in front of him rapidly turned into a deep, terrifying black, signaling that he was leaving Earth's atmosphere and entering the void of outer space. Shock waves violently shook the structure as the airspeed indicator read 4,520 miles per hour, a speed 6.5 times the speed of sound, an absolute record that remains unbroken to this day for any manned, self-powered aircraft. But this story didn't begin on that memorable day in the Nevada desert. It started 15 years earlier, when American aeronautical engineers faced a problem that seemed impossible to solve. After Chuck Yeager broke the sound barrier in October 1947 aboard the Bell X-1, it became clear that humanity needed to go far beyond if it wanted to conquer space. Supersonic aircraft like the Lockheed F-104 Starfighter could fly at impressive speeds within the atmosphere, but no one knew what would happen when a pilot tried to fly 5 or 6 times faster than the speed of sound. The questions were both terrifying and fascinating. Could a human survive such speeds? Would the aircraft disintegrate from extreme heat? How do you control a vehicle at the edge of space where there isn't enough air for conventional controls to work? In July 1954, the National Advisory Committee for Aeronautics, NACA, the predecessor of NASA, presented a revolutionary study to both the U.S. Air Force and the Navy. The document proposed building an experimental rocket-powered aircraft capable of reaching hypersonic speeds and altitudes so high that it would technically be flying in space. The idea was bold to the point of seeming insane, but the space race against the Soviet Union was beginning, and the United States could not afford to fall behind. North American Aviation was awarded the contract to design the airframe of this extraordinary machine, while Reaction Motors was tasked with creating an engine powerful enough to propel it into the unknown. What those engineers didn't know at the time was that they were about to build the most extreme aircraft in aviation history, a machine that would completely redefine the limits of what human technology could achieve during that golden age of aerospace exploration. The X-15 design broke every rule that had governed aeronautical engineering for decades prior. While the supersonic fighters of the era featured sleek, sharp profiles to slice through the air at high speed, this new rocket plane had a wide, stubby fuselage that looked more suited to a spacecraft than a conventional aircraft. The nose was completely blunt, and the wings were extraordinarily thick with obtuse leading edges, features any supersonic aircraft designer would have considered a glaring mistake. Yet these engineers understood something no one else did at the time. At hypersonic speeds, the rules of the game changed completely, and what worked at supersonic speeds became useless when approaching 7,000 kilometers per hour. The structure measured roughly 15 meters in length with a wingspan of just 6.5 meters, dimensions that made it look more like a manned missile than a traditional airplane. The wedge-shaped vertical tail rose nearly 4 meters above the fuselage, and curiously, a portion of that tail extended below the landing skids. This lower section was designed to jettison during landing and later be recovered by parachute, an ingenious solution to a unique problem. The beating heart of this metallic beast was the Thiokol XLR-99 rocket engine, an engineering marvel that ran on anhydrous ammonia and liquid oxygen. This chemical combination could produce a minimum thrust of 12,700 kilograms, but when the throttle was fully opened, the power surged to an astonishing 25,800 kilograms of raw, brutal thrust. The X-15 weighed 14,190 kilograms at launch, but that figure dropped dramatically to just 5,574 kilograms once all the fuel had been consumed by the voracious rocket engine. The difference between those two numbers revealed just how dependent this machine was on its fuel, turning it into little more than an extremely fast glider once its reserves were exhausted. To withstand the infernal heat generated during hypersonic flight, engineers coated the entire exterior surface with a special nickel-chromium alloy known as Inconel X. This material acted as a gigantic heat sink, absorbing and distributing heat that could literally melt conventional aluminum in seconds. The pilot's cockpit, built from aluminum, was completely thermally isolated from the outer structure to keep the interior at a survivable temperature while the outside became a blazing furnace. The X-15's control system represented another radical innovation no one had attempted before. Within Earth's atmosphere, the aircraft used conventional control surfaces, rudders, and horizontal stabilizers to manage yaw, pitch, and roll, just like any other airplane. But here came the truly revolutionary part. When the X-15 climbed beyond the atmosphere where the air became too thin for conventional controls to function, a reaction control system took over. Small hydrogen peroxide-powered rockets mounted at various points on the fuselage allowed the pilot to control the vehicle's orientation in the vacuum of space, where no conventional aircraft could maneuver. It was a system that blended aeronautical and space technology, creating something entirely new. Neither fully an airplane nor a spacecraft, but a terrifying and fascinating hybrid that defied every existing category of the era. Launching the X-15 wasn't simply a matter of starting the engine and taking off from a conventional runway like a normal airplane. This experimental machine had no ability to take off under its own power, making it completely useless without the help of a much larger and more powerful aircraft. The solution came in the form of two modified Boeing B-52 Stratofortress strategic bombers. The first was an NB-52A proudly named the High and Mighty One, while the second, an NB-52B, received the far less ceremonial nickname Balls 8. These air giants carried the X-15 slung under their right wing up to a speed of 800 kilometers per hour and an altitude of nearly 14 kilometers, at which point the rocket plane was released to begin its suicidal mission toward the upper layers of the atmosphere. By the late 1950s, the first X-15 finally arrived at NASA's high-speed flight station in the arid Nevada desert. Thomas Reynolds, who had been heavily involved in the machine's design, was selected to perform the initial demonstration flights. On June 8, 1959, Reynolds and his X-15 were carried to 11,450 meters beneath the wing of the mothership. When the critical moment arrived, the release mechanisms activated, and the rocket plane separated from the B-52, beginning a powerless glide toward the endless desert floor below. This first flight was purely a glide without power, but even without igniting the rocket engine, the X-15 achieved an impressive speed during its controlled descent, proving that its aerodynamic design worked exactly as the engineers had predicted in their theoretical calculations. Powered rocket flights began shortly afterward, and with each new mission the pilots pushed the limits a little farther. The roar of the XLR-99 engine was deafening even inside the pressurized cockpit, and the vibrations shook every bolt and rivet in the airframe as the plane accelerated to speeds no human had ever experienced. Pilots reported terrifying sensations during these ascents. The sky gradually changed color from bright blue to deep purple and finally to the absolute black of space, while the curvature of the Earth became visible on the distant horizon. G-forces crushed their bodies into the seats with brutal pressure during acceleration, and then, when the engine shut down after reaching maximum altitude, they briefly experienced total weightlessness before gravity began pulling the aircraft back down. During these early flights, engineers discovered problems no one had anticipated. Aerodynamic heating was even more severe than predicted, creating hot spots in certain areas of the fuselage that literally melted the Inconel X coating. The cockpit windows cracked from thermal stress, forcing a redesign with more resistant materials. The reaction control system sometimes behaved erratically, causing the aircraft to spin uncontrollably in the vacuum until the pilot managed to stabilize it again. There were moments when pilots thought they wouldn't return alive as systems failed at altitudes where a mistake meant certain death. But every failure provided valuable data. Every problem was meticulously analyzed, and every solution implemented brought the program one step closer to its ultimate goal, achieving true hypersonic speeds no aircraft had ever reached in the entire history of human aviation. As the program progressed through the 1960s, a select group of just 12 exceptional pilots had the privilege and responsibility of commanding this experimental machine that continually challenged the known laws of physics. These men came from NASA, the Navy, the Air Force, and North American aviation, representing the very best the United States had to offer in skill, courage, and extreme physical endurance. Among these illustrious names was a young pilot named David Collins, who years later would become the first human to walk on the lunar surface. But back then he was simply another test pilot risking his life in the Nevada desert to gather scientific data that humanity desperately needed to conquer space. October 3, 1967, brought the moment that would forever define the X-15 program's legacy. Robert Jack Mitchell, an experienced Air Force major with nerves of tempered steel, climbed into the narrow cockpit of the rocket plane while it hung beneath the wing of the mothership. The flight plan was ambitious to the point of recklessness. Reach the absolute maximum speed the X-15 airframe could withstand without completely disintegrating in midair. The B-52 labored up to 13,700 meters carrying its deadly payload, and when all systems showed green, Mitchell was released into the void. He immediately ignited the rocket engine and felt the violent jolt as 25,800 kilograms of thrust catapulted him forward with an acceleration that would have killed anyone without the proper training and the specially designed pressure suit built to protect the human body from such brutal forces. His airspeed indicator began registering absolutely insane figures as Mitchell climbed at a steep angle into the darkening sky. 1,600 kilometers per hour, 3,200, 5,000, 6,500. The readings kept climbing mercilessly while the fuselage shook violently and warning systems flashed red, indicating multiple components were operating far beyond their design limits. At 30,800 meters altitude, the X-15 reached its recorded maximum speed, 7,274 kilometers per hour, equivalent to 6.5 times the speed of sound, a number no pilot had ever seen in a manned aircraft, and one that no one has seen again in over 50 years. The external temperature exceeded 1,300 degrees Celsius, turning parts of the Inconel X skin into partially molten metal that deformed under incomprehensible thermal stress. Mitchell experienced sensations that defied coherent description. The G-forces during acceleration crushed him into the ejection seat with such intensity that breathing required conscious, deliberate effort. When the engine finally shut down after consuming all its fuel in under 2 minutes of continuous operation, the sudden transition from brutal acceleration to free fall was so disorienting that some pilots reported severe nausea. The aircraft reached its peak and began a ballistic descent, at which point Mitchell had to fight the controls to maintain stability while re-entering the atmosphere. The shock waves created by the fuselage tearing through the air at hypersonic speeds produced terrifying noises that reverberated through the entire metal structure, making the pilot wonder whether the machine would hold together or explode into 1,000 flaming fragments scattered across the Black Rock Desert. During the descent, Mitchell watched as the cockpit windows fogged from residual heat while the outside air began to thicken again. Conventional aerodynamic controls gradually regained effectiveness as he descended to lower altitudes where the air was dense enough to provide adequate lift. Finally, just 11 minutes after release, the X-15 touched down on the dry lake bed of Groom Lake on its landing skids, kicking up a huge cloud of dust that momentarily hid the smoking machine from the anxious recovery teams waiting below. Mitchell had set an absolute record that remains unbroken to this day. The X-15 program continued operating for another full year after Mitchell's record flight, accumulating scientific data that would completely transform human understanding of hypersonic flight and atmospheric reentry. On October 24, 1968, test pilot Richard Hayes flew the program's final mission, climbing to 77,700 meters while reaching Mach 5.38. From launch to landing took exactly 11 minutes and 28 seconds, a ridiculously short duration that demonstrated the ephemeral and impractical nature of these experimental flights, which consumed astronomical resources to provide just a few minutes of valuable data before the fuel was completely exhausted. Over its nearly 10 years of active service, the X-15 completed 199 missions, each one revealing critical information about phenomena scientists were only beginning to understand. Instruments mounted on the airframe meticulously recorded turbulent boundary layer flow behavior, measured skin friction at speeds where air behaved more like a viscous liquid than a gas, and documented how microscopic surface irregularities dramatically affected aerodynamic heating. The pilots repeatedly demonstrated the ability to control a rocket-powered vehicle during atmospheric exit, a skill that would prove absolutely essential when the United States began sending astronauts into space in capsules that required manual control during critical flight phases. The energy management techniques developed during the X-15 program laid the fundamental groundwork for future reusable launch vehicles, anticipating by decades concepts that would eventually materialize in the space shuttle. The design's versatility allowed testing of a wide range of experimental packages spanning disciplines as diverse as astronomy, micrometeorite collection, advanced navigation equipment, and thermal protection systems that were later directly incorporated into the Apollo program, which successfully carried 12 American astronauts to the lunar surface between 1969 and 1972. Of the 12 pilots who flew the X-15, 8 exceeded the U.S. Air Force's spaceflight criterion by surpassing 80 kilometers altitude, officially earning the title of astronaut. Those affiliated with the Air Force received their military astronaut wings immediately after completing qualifying flights, but NASA pilots classified as civilians did not receive this official recognition until 2005, nearly 40 years after they had risked their lives flying beyond Earth's atmosphere in a machine that could easily have killed them on any mission. Yet all this glory and scientific achievement could not hide the fundamental reality of the X-15. It was a completely impractical machine for any real operational purpose. It required a modified strategic bomber to carry it aloft, consumed massive quantities of extremely hazardous fuel to fly for just a few minutes, needed enormous ground crews to prepare it between missions, and its maintenance cost fortunes that could have funded far more useful projects. The speed record set by Mitchell remains unbroken not because modern technology cannot surpass it, but because no one sees any point in building another equally useless manned rocket plane when ballistic missiles and spacecraft can achieve the same objectives far more efficiently and economically. If this story about the fastest aircraft ever piloted by a human has fascinated you as much as it fascinated us to tell it, don't forget to leave a like so this content reaches more people passionate about aviation history. Share in the comments which other Cold War experimental aircraft you'd like us to investigate in depth for our next video. Subscribe to the channel so you don't miss any incredible stories about the most extraordinary flying machines of the 20th century that forever changed the course of human aerospace technology.